let's go to this. Actually, no. This one right here. There we go. Okay. Welcome to the stream. Looks like my mic's working well. We got good audio there. Okay. Visuals look good. We're not going to have any, I don't have a real board with me to look at, so it's just going to be my face as we talk about this. So I thought I was going to share an experience I had, or a project I had to do recently. So Avnet has these KU40 boards, and I recently, for my PhD research, had to put Linux-on-Litex on these boards. And it was a relatively simple process to do, and I just kind of wanted to go through what I had to do to get it up and running. And I didn't do fully features. I mostly just targeted DDR, Ethernet, and SD card, PMOD SD card interface, which all worked in the end. And it took me like 24 hours to get it up and running and test it thoroughly. There was a few hiccups, mostly with some ultra-scale features. I don't think the ultra-scale features have been really fleshed out on Litex. They're mostly targeting Series 7 boards or other vendors. So here we're going to go and just walk through what this was. And it looks like we have someone in the chat. Hello. Nice to see you here. I'm glad you could join us. We're not gonna do that today. So I guess, I don't know why this is called Vertex C. So let's just walk through this board, what features are on this board. Yeah, this is probably a great one to look at. So we have the KU40 board. We have the DDR, a bunch of QSPI flash, standard USB UART, LEDs put switches, all good stuff. Never used a PC4 connector before. We have an HDMI connection, which is pretty cool. It's going through an HDMI interface. I wonder if that's doing decoding. We have two RJ45s. Some other interesting things. Quad port PMODs. Yeah, they all work pretty well. So yeah, everything worked pretty well. Here's the board. So Avnet mysteriously stopped making these. They ran for like a year and a half, and then Avnet discontinued it. All I can think of is that the power regulators sometimes failed. There was a flaw in their design or something, because we purchased 3 boards and only 2 out of the 3 boards worked. The other one, the lights didn't all turn on for the power regulators. So is it well designed? That's a good question. I probably would have to review the schematics to make sure it's well designed per se, but it was a very convenient board. We've done a lot of interesting tests with it. I really hope that I wish there was a board like this. I've thought about, like, I have the schematic. I can make something similar. I'd like to do a KU60 version of it, but we just don't have the time or the manpower or the expertise to do a very good PCB this way. Okay, where was that? We talked about the PC4 connection. I just was curious what the PC4 connector was. Unless they were talking about the HPC FMC, which I don't think they were, right? The FMC, yeah. I don't know what the PC4 is. We're going to go look at the PC4. I'm curious. PC4 header. Oh, it's right behind the Digilant JTAG. Let's see. Oh, I got to go. That wasn't very smart. Let's go back to the picture. I want to see what's on the back of the, right behind the, oh, it's just talking about the raw JTAG. I guess PC4 is the raw JTAG. Okay, so that's why the arrow is connected there. So let's walk through how we got this board going. So first, I forked all these repositories. I'll list the repositories later so people can follow along. But this is the Linux-on-Litex Vectress 5 repository. This is kind of where they have a huge list. This has always impressed me, right? So you can have Linux running on a soft-core processor within minutes. Not minutes, but and you can use open source tools, you can use vendor tools. They have a lot of cool options here. And I've done this on the Acorn. I've done this, I think, on the RD board, the KCO105 board, the ZCO104. I don't think I've done it on the ZCO104 board. We've done it on the Nexus DDR, the Nexus Video. think I've done that one. I think I've done the on the BCU 1525, which is the same board. Do badge. I've done it on this one. I've done it on the Orange Crab. Yeah, I think that's it. But they support Intel, Lattice, Xilinx. So a lot of interesting stuff being done here. You can build everything from the FPGA image to the Linux kind of build root-ish Linux image. We've been able to run Drystone and CoreMark on these systems, and they support Ethernet, SD card, serial booting, and it's been very impressive so far. I have no complaints about this repository. So we have this new board, and I need to figure out how to add it. So it's basically, you know, look at the existing boards and copy and paste and change it to what it needs to look like. That's the majority of what happened here. So using, you know, the whole pinout here, I looked at the user guide, I looked at the schematic. I have all the information I need to use to build a new board with the user guide and schematic. So let's look at my my commit for this one. Okay, so we have 2 commits for this one. So let's look at my 2 commits. So we're gonna look at the first commit and the second commit. I think the second one, yeah, that was a fork. We don't need to worry about the second one. So the first one is where I add the AES-KU040 board. It's not Litex boards. No, we want to go here. Commits. Move 50 clock to work. Okay, so we're gonna look at this repository real quick. So this is how easy it was to add the AES-KU040 board. So, I mean, we're just going to be looking at this right here. It thinks I copied it. So we'll go look at the file directly in a second. But I copied the KCU105. I mean, it's running a very similar chip. I set the baud rate to this because the KCU105 had an issue, and I assumed this design copied the KCU105, so I didn't want to push the baud rate. And we have serial and Ethernet, and I wonder if there's an SD card there. I'll have to maybe have to look at that file in a second. Then it's as simple as copying it to later where the other boards are listed and adding it down here. Oh, here's where I added the SD card PMOD IO option, as I saw with the Artix board. So I kind of just copied the Artix board for adding the SD card PMOD option, and I'm just using the Digilant PMOD to do booting off of the SD card. So that's all I had to do on Linux-on-Litex. Then I had to create a board. So we're going to go to Litex boards. So the Litex boards repository has all the board support. And accelerator boards, repurpose boards, development boards. So great selection. Not all of them supported by the Linux-on-Litex, but a lot of them. And there's 2 sections. So we go to Litex and boards. We have platforms and targets. So the platforms, if I believe correctly, is the pinout of the FPGA. So yeah, this is a Python description of the pinout of the FPGA. And we're going to look at the Xilinx AES-KU040 board. That's what I called it in this situation. So we'll look at that one in situation. And then the second directory is the targets. So we'll look at the video one real quick. Next is video. So the targets, could you please show it for the U-boot and kernel repos? So I didn't have to change U-boot or kernel repos. I'm using the same default U-boot and kernel that runs on all the other Linux-on-Litex boards. You build it, we can jump back real quick to answer that question. It's a quick question. So, and the way you can build the U-boot and the kernel is down here, generating the Linux binaries, optional. And you can go through, clone the build root, and you can make it and target the external here, like defconfig and make. And then in here you can go edit the kernel, the U-boot, and whatever you need to do to get it working. But I didn't change it at all to support this new board. Because we're doing a soft system on chip, it matches exactly I mean, there's some address changes and whatnot, but there's the we load in kind of a device tree when we boot up. So we're just kind of changing the device tree that the Linux image references. So it's very easy to kind of make a new board, change around the peripherals, and have it work immediately. So I didn't have to generate a Linux image. I used his pre-built binaries. So that's a good point. I should probably talk about that. So if you go to his pre-built, so he has pre-built images somewhere. I'll have to hunt those down at some point. But he has pre-built Linux images and other things that you can use. And it's great. Works off. So we're just working on the hardware design. So back to here, we have the targets. So inside the targets for Litex boards, this is basically a Python description of the system on chip, the block diagram and kind of Avado terminology. Where you define your clock system, your video, base sock, and you can have extensions on it where your flags to add things, to remove things, the processor, the DDR, the Ethernet, SATA, PHY, or the whole SATA core, video, LEDs, and this, and I think there's they have right here we can add an SD card option. So this is their Python that then they can configure when they build for various different options. So let's go ahead and talk about the AES-KU040 version. So first we're going to go to the platforms. As I repeated earlier, I didn't use all of the features that are available. We definitely could support those features with a lot of the peripherals that already exist in Litex. But for my test, I needed some specific peripherals. And so that's what we set up. We have the clock, the reset, the serial. So this is a GMII, not MMII. It's a GMII interface. So if we go back to here, and we go to Ethernet. And where do they talk about the Ethernet? Right here. Ethernet PHY interfaces. And I just kind of looked at this interface that is using different settings off of these Texas Instrument boards, right? Yeah, Texas Instrument devices. I had to read the documentation, understand how it kind of worked a little bit. But unfortunately, there were some peripherals that already handled it. So we added the pinout for the Ethernet. I really like how you can just take one data pin and just kind of list all the pins right here. You can also do the IO standards. You can do custom little miscellaneous features. I tried to do IOBs on some of these signals and they kind of failed. But we have the address pins, bank. This is bank group. I don't remember. Is that just bank address? Maybe. Here are the other address pins. They're duplicated. Kind of want to use these two pins later on. I need to figure out how to add that feature, but we'll figure that out later. All the other data signals, clock, and okay. So that's what we did. We've now added these pinout for our board. I also added PMOD 0 and 1, and we can do a raw PMOD signal, which kind of acts as a GPIO. And then on PMOD 0, this is where I set up the USB PMOD IO. USB to UART interface. Oh, we're not doing that one. We're doing these are all different PMODs you can use. And right here I have the SD card PMOD. I just kind of copied this from another PMOD thing. But it was very easy to just copy and paste this from the other examples to get it up and working. And then yeah, this is kind of just copying everything. I need to set the internal vref for those banks. I had to look that up. Yeah, that's about it. Toolchain, Vivado, put the board in there. So very, very straightforward. I mean, mostly just copying and pasting, reading the documentation to add this. It'd be interesting if we could be able to take a XDC file and generate one of these from an XDC file, but for Xilinx tools, but that's not really how it works. So now we're going to look at the platform here. And yeah, mostly copying just interfaces. We have a KU we're using that for the PHY interface, or the Ethernet PHY interface, but that's pretty basic. I didn't really use the LED chaser, but we have that working. So we have our PHY. We have a CPU reset. Our clock in's to 250. We're going to generate a our sys clock, which should be defined. It's defined somewhere else, but our sys clock is 100 megahertz. So this can create a 400 megahertz clock. It's going to create an I delay and Ethernet clock speed as well at 200. Add some false paths. This is critical for getting some good timing. Then we have a buff D. These are our primitives within Vivado that help us to bring in that that differential clock. So this brings in a differential clock, and this allows us to just put a buff G on it. And what was the input of? It's just this clock. Okay. There's I delay controls for the Ethernet, and we just grab the platform that we just built. We have an Ethernet IP. We want to do the core, and we'll just add all that useful information. Ethernet, we're calling the RGMII because it's an RGMII interface, not a SGMII or RMII. So we call that feature, and we just add the clock and the pads, and we just add it to, and it's able to pick up all the pins from the pick up the pins correctly from our platform. Then we add the DRAM. The DRAM was relatively easy to add. It's the same one on the KC01005. I just had to cut the size in half, or the address size in half, and it understood it pretty well. Anything else fancy in here? Nah, not really. So that's all it kind of took. Mostly just copying and pasting, changing a few values. So there was a few hiccups with this as I was working through this. And to get this running, so the first hiccups was that Vivado did not like the timing of the I delay controls. Basically, what's happening because of the clock and the differences between the Series 7 I delay and the ultra scale I delay, we were going beyond beyond the settings that were available for the I delay. So I kind of had to shorten that time a little bit. So we went to going to the light Ethernet. We can go look at my little commit here. And all we're doing really here is we want to, unfortunately for light Ethernet, the rep clocks were hard coded. So I needed to change the hard coding value to 200 to match my implementation. And then we needed to change the delay because these delays were too long for the ultra scale I delay primitives. So I had to change that. That's all I had to do. Just basically I read the Vivado report when place and route failed, try to find the nets that were failing, try to figure out the better solution. So this is a lot of going through re-implementing on Vivado, looking at the errors, trying to resolve it. The second issue is that the SD card feature was not working, and this deals with the tri-state. So so if we go to Litex, the normal one, and we go look at this last commit, there's a tri-state signal. They use what they call it single data rate tri-state. So we have an output and an input. And before, they were just calling the DDR output. And this was kind of difficult to look at because the SDR, DDR primitives for Series 7 and Ultra Scale are very different. And you can't really do SDR well. I mean, there's instructions how, and I tried to follow the instructions and it failed. And after looking through some MyGen examples, MyGen uses a flip-flop and it puts the flip-flop in the IOB. So instead of doing a fancy ODDR interface primitive to get the SDR working, I just needed a simple tri-state to be able to read the SD card. And because the SD card is low enough clock rate, it's not a big issue. So what we did is I put a flip-flop here. And basically, yeah, I replaced the ODDR with a basic flip-flop. And there were several issues. I tried to do the IOB setting. What do you call that? The attribute. I tried to add the IOB attribute to various things within various signals. I tried to add it to the input, the output, the tri-state signal. I tried to add it on the pin level. And it either didn't detect it and didn't put an IOB on any of the signals, or the IOB crashed because it was trying to apply it to too many registers. Because I did on the pin, it tried to apply it to all three, and you can only have the input, output, tri-state, and you can only have the IOB on one. And when I tried to do it at the HDL level with the little Verilog attribute, even manually and automatically, the report data sheet. So in Vivado, you can do the tickle command report data sheet, and it'll give you the skew of your inputs and outputs of your I/O, and the skew was not good enough. The skew was obvious that these signals weren't in an IOB, but luckily with the low clock rate, that skew in the report data sheet didn't really matter. So added a flip-flop, and the SD card boot started working. So these are the only changes I had to do to the Vex, or the Linux-on-Litex Vex RISC V, to get this up and running. I will post these repositories if anyone has these boards, but in all honesty, if you do have these boards, I'm looking to get some more for my research. They're discontinued and they're hard to find. But hopefully this introduction can help you look at these examples to be able to add your own board, to be able to add it, and if it's not supported, it's not a big deal to add your own board to it. And then I just used the pre-built Linux images. There's a few files that he provides, and I'll have to look it up at some point. There's a few files he provides. He provides the Linux binaries, this binary, and you're able to boot it up. And it's great to see it go through the U-boot process, load the image from SD card, and then get the Linux running. And then you can ping over Ethernet. So I proved that all my features work, and it was a success. What I hope to do in the future, moving forward, I'm going to try to build on this a little bit. I'm going to try to get the DDR ECC working, which is a little bit of an issue because the DDR is only 32 bits wide. So we're going to have to do an awkward size. Maybe do like 24 bits data, 8 bits, well, 24. We'll have to do 7 bits ECC. That's going to be kind of awkward. But we'll find a way where we can do a portion of the DDR data as data, and then the error correction codes. And there's support for this in Litex. I have to go play around with it. I also want to use for my test, I want to look at the parity errors on the address and command lines for the DDR. So we go pop the DDR. So there's a alert and a parity signal, and if you enable this, it will check for parity in your address and command lines. And this is useful if they're like when I do radiation testing and whatnot, that we can have single point failures in the OSERTs of the address and command lines. And that's not something ECC can fix. And if these single point failures are causing our design to fail, and we want to find ways to mitigate it, the parity may be a low cost option that may help us to at least detect and maybe do rewrites or try to transactions again after we have repaired the FPGA. And I think that's it. Those are the main features I'm looking at adding over the next 6 months-ish. We'll see how that goes. And do testing on that in the future. If anyone has these boards, kind of reach out to me. I'm trying to look for some. I think it's a great board. I think there may be some issues with it, but so far it has proven to be useful. Thank you for watching the stream. How are we doing on time? I think it was a good time. Yeah. So I'm going to update the repositories, and I think I'm going to post this on Twitter. I want to see what the main group that does the Linux-on-Litex, I want to see if I can get their opinion. But that's it. Thanks for watching. Join in tomorrow. We're going to try to go through a PyTorch example on Vitis AI. Hopefully it works well.